recorder? Okay. It's absolutely delightful to be here, so thanks, Piero, for inviting me. I am a mathematician, and you may not associate mathematicians with people that love art, but I happen to think that mathematics is the most beautiful thing on earth. And I want to convince you today that that's the case. Now, we're going to use a few tricks, so we're not just going to stare at equations. I get really a wonderful feeling inside of me when I stare at a system of equations, but I'm not expecting you to have that same sort of feeling. So what I'd like to do is provide some color and some illustrations of systems of equations. Now, what are matrices, you know, and why, as a mathematician, do I love them so much? Well, let me just give you a little bit of a feel of what sort of problems I work on. I'm a computational mathematician, and I really like things to do with fluid flow. So you give me a fluid, I like to simulate it. So I've done work on coastal ocean flows, I've done work on oil and gas flows in reservoir, I've designed sails for the America's Cup, for those of you who know about the America's Cup right now, not for this particular race, but in 2000 and 2003. But all of these things, and when it flows, I'd like to simulate it. And to simulate this, we set up a really large system of equations relating pressures at all sorts of different points in the flow field and velocities, and we need to solve it. And ultimately, the system of equations leads to something called a matrix. I'll show you an example. But also, because I like matrices so much in these matrix equations, I can use that same knowledge to help, for example, with the design of a search engine or a recommender system. And that may sound really funny to you, but it's exactly the same math behind it. And the math behind it is this matrix stuff. Now, for some of you, matrices may actually have to do with something like this. Do you recognize that made with the movie The Matrix, which I happen to love, but has nothing to do with my field. But if you type in matrices, or you type in matrices for engineering applications in Google, you get millions and millions and millions of hits. And you can see lots of different applications that somehow use this. This is just a snapshot of the images, the first space of images that you will see when you type in matrices. And when you go look at this, you see matrices come up in flow mechanics, but also in structural mechanics. You see it come up in social networks. You see it come up in neurology, you know, biology. So many different application areas use these matrices. And so visualization of them is nice also because sometimes, you know, when we stare at a big matrix, which is just a table with numbers, it's very hard to discern patterns. But sometimes when you start visualizing them, you can get a deeper understanding also of the underlying math and the underlying physics. So let's start with a little bit of algebra. So say that I have 4 unknowns that I want to compute. Now, so this brings you back maybe to high school algebra. If I have 4 unknowns I want to compute, in this case they're called W, X, Y, and Z. We always use these sort of variables because mathematicians we're not that creative, right? So we use things like X, X1, X2, X3, and so on, right? And if I want to solve for 4 unknowns, I need 4 constraints, 4 equations that tell me how they relate to each other. And here I just made up 4 of those, okay? Now, one of the things that you see is that there's some empty spots here. And you see, but you also see that there is this pattern, W, X, Y, Z. They're always written in the same pattern. Sometimes there's a 1 in front of it, 1 times W, 1 times X, and sometimes there's nothing, which really means there was a 0 in front of it, right? But as a mathematician, I look at this, and I'm a very organized person, so I write all these things in this particular order, and I see there are 4 equations, and each equation has a bunch of coefficients corresponding to W, bunch corresponding to X, to Y, and to Z. And all I really need to remember for the system is these coefficients, right? As soon as I fix the order, all I need to remember are these coefficients. So what I'm going to do is I'm going to rewrite this a little bit, and I'm going to create this table here, which has these coefficients. Now, I left out the zeros. Now we're also very lazy mathematicians, so zeros we never write down. Also because with these large system of equations that we often deal with, say for a recommender system or PageRank or search algorithm, there are many, many, many zeros, so we leave them out, right? But arguably, all that's really important to me for this particular system, whatever that represents, maybe it's pressure and velocity relationships in the fluid flow, maybe it's a friend networking algorithm, I don't really care. All that's really important is this table with numbers. This table that we call a matrix. Okay, so that's the matrix. Now, sometimes we use very simple visualizations. One is called a spy plot. And all I do is, I had all these ones, and everywhere a 1 appears, I simply put a little dot. Okay? So in this case, I'm not so interested in what size these coefficients are, whether they're 1 or 2 or 10 or minus 200, I don't really care. I just want to know where there are non-zeros. Because these non-zeros give me exactly how these things relate. If I have a non-zero right here and a non-zero there, I know that W and Y were in an equation together. And so the pattern of these non-zeros give me information about the system. Does that make sense? And so the simplest way, because again, we start this very simple and not super creative in the beginning, we just put a little dot. And then for very large systems of equations, we may get things like this. So this is called a spy plot. So this is just a matrix with dots wherever there are non-zero. And you see that there are patterns now that I can see. And actually these come from a network. A matrix can also represent a network, which we'll see in a little bit. And they're Stanford networks. This is, I think, Stanford as a whole. And this was the internet and all the pages in AeroAstro that we crawled in 2004 to create those spy plots. And looking at this, I can see, because I know a little bit about how these things were created, that here are clusters of websites that are correlated very strongly, so they keep on referring to each other and internally, and then they're not very much connected to this, so that's central administration, right? They only talk to each other, not so much to others. And I can look at this and I can discern organizational structures, and it's amazing how you can use these things, right? And then, of course, some other equations may lead to more interesting patterns. This is a spy plot of a particular equation, a system of equation that I looked at in oil reservoir modeling. And when I look at these particular patterns, I can say something about the behavior, not that much, but it's still reasonably pretty. And then what I could do is, if the actual non-zeros changed in size, so some of them were bigger than others, I could give them a color depending on their size. Right now we're getting very arty for a mathematician. This is pretty amazing, right? And I get things like this. Now there are many more interesting ways to do this, though, and this is really what I'd like to show to you today, is to use graphs. So we're going to go back, I hope, to this matrix, okay? Now I want you to focus on the, in this equation here, this equation had W plus 0 times x doesn't play a role, plus y plus nothing times z is equal to 1. That's really where that came from. And from this, I know that there is a connection between w and x.
Why?
Right? They're in the same equation. Right? W and y, sorry. W and y. I thought you said y. So I think I tried to explain it again. Because there is an equation connected. Okay. But w and y. So all I'm going to remember now that there is that connection. Now W is here in this location, Y is in this location, and this non-zero I can see as really connecting those two together. Okay? So if I say I have a non-zero at the first row and the third column, I know that W and Y are connected. If there is a non-zero, say, in the second row and the fourth column, I know that X and Z are connected. That's what I'm going to do. So I am just looking at these non-zero, these ones off this diagonal. The diagonal is sort of saying W is connected to itself, but this one signifies a connection with W and Y, this between X and Y, and so on. And so when I look at those non-zeros, I could also write it like this, as a little graph. Now I see 1 and 3 are connected. The first element and the third element, that was the W and the Y. Now I measure W, X, Y, and Z. 1, 2, 3, 4. And so 1 and 3 are connected. There is another equation that connects 2 with 3, and there is an equation that connects 2 and 4, and there is an equation that connects 3 and 4. These are the connections that I have between these unknowns. Now I made it very abstract, right? Because I had this system of equations that told me exactly what these connections were, and I'm just removing that and say, I'm just interested now in connections. What is influenced by what? If W and Y are in an equation together, then the size of one influences the size of the other. And that's all I'm interested in now. Now vice versa, if I had a network like this, a connected graph, maybe friends, friend 1 is connected to friend 3, and 3 is friends with 4, but 4 is not friends with 1, then I could replace that network, this graph, with a matrix. Right? I could go from one to the other. But now I'm going to take these matrices, maybe they come from fluid mechanics, and I have 10 million columns this way, and 10 million rows this way. This is what we call a small simulation. Okay, so I have a lot, and I'm going to create a graph out of that, right? Now when I look at that graph, I can see these connections, but of course you immediately say, well, I can draw this in all sorts of different ways. These are the same graphs, just drawn a little differently. And then the question is, well, which drawing do you prefer? Which makes it clearest what the connections are to you, just by looking at it? What do you think? This one? Yeah, I like this one a lot too. So then, of course, this is just with 4, right? I just have 4, 1, 2, 3, and 4 in connections. Now, suppose I have 10 million, with maybe 50 million connections total, and I ask my student, make me a nice looking graph. So they can look at it and discern a little bit of information about fluid flow, right? So that would be very hard to do by hand. So if I had something like this, and I say, well, give me something that looks really good, right? Because now there are all these overlapping connections. So then it's an interesting thing. So how do I pull apart this complicated looking graph, this mess, and make something where structures and connections are much more easy to see? And that's what I want to show you, because we can do this. Now, you may say, this is a made-up example. Who has a messy network like this? So let me just show you just one example that I just got off the web. I just looked at work by Alaric Hall, who looked at sagas from Iceland, and he published this. Okay, so these are the connections between various sagas. So obviously this is very messy, and I think he should be using our software. Right? So maybe I should send it to him. So these things happen. So now the question is, if I have a bunch of nodes, right? So now I just placed some nodes, 1, 2, 3, 4, all the way to 10 million, and I have connections between them. How do I figure out how to pull them apart and put them on a two-dimensional piece of paper so that I have a nice view? Okay, so how would you do it?
Grab one and pull.
Somehow you need, first of all, you need two nodes that are really strongly connected to come close, right? So if node 1 and 2 are strongly connected, maybe because there was a big non-zero in this matrix, then I want them to be close, right? And if 1 is connected to 2 and 2 to 4 and 4 to 17 and 17 to 300, I don't want 1 and 300 to be too close because there's 4 degrees of separation. Right? So the question is, how do I do that? Now here's the trick. Here's the trick. So we have these nodes and we have these lines connecting them. Okay? Now what we're going to do is two things. Each of these lines, we'll imagine it's a spring. So when we pull things apart, they pull back, right? And the size of the spring, the strength of the spring, guess what? That's determined by what? By the size, the strength of that non-zero, right? Okay, so that's nice. But I don't. What would happen if I did this? I had all these nodes and I put springs on them, and then I let it go. What would happen if I didn't do anything else? Would just all get together. I don't want that either. I don't want them all to cluster. So they're not allowed to get too close. So how can I make things? No, I need some sort of repelling force. When they get too close, they're not allowed to. So what do? I give every node, which imagine a little ball, I give them an electric charge so that they repel each other. Okay? So now I have a whole network of balls attached to springs. The springs have stiffness. The balls have an electric charge. And I just let the whole thing drop on the floor.
Want a glass of water?
Oh, thanks. So I let the whole thing drop on the floor. Because I want it two-dimensional, right? And I let this thing organize itself so that it comes to an equilibrium shape, and that's always minimizing some sort of energy, right? It's beautiful. These systems do this automatically. And it just let them organize themselves. So it would look something like this. We start with this, and we let it drop, and out comes this.
Wow.
So that's exactly that same configuration. Now, here, we've cheated a little, or cheated. How big you make that electric charge and how big you make the strength of these springs, that determines what stuff you get out. So often we need a lot of twiggling to get it to look really beautiful. Okay, so this looks really easy, but some of the pictures that I'm going to show you took a long, long time to create because there was a lot of twiggling. Well, put a little bit more spring strength here and a little bit more repulsive charge there. But when you look at this, it's beautiful structure. And it shows you very naturally these clusters. And when you stare at these clusters, you can really get some information of the underlying system out, no matter where this comes from. Isn't that nice? Now let me show you some really beautiful examples, much larger systems than this. This is a financial portfolio optimization. So this is a matrix that comes up in one of the simulations or computer programs you would have for financial portfolio optimization. This looks much better than what you would imagine from the 2008 problems, right? I mean, how did we know that this was behind it? This one is another type of program that we often have in optimization called quadratic programming. It's the matrix from one of those simulations, and here is a close-up. So they're very intricate things. Now again, these are just two-dimensional patterns, right? But of course it looks a little bit three-dimensional here. You can also do these things in 3D, but it is much harder to visualize. This one is from electrical engineering. It's a circuit simulation. So we also affectionately call this the porcupine, right? And this is a close-up. It's not super high-resolution image, but it gives you an idea. This is another linear programming problem that comes from some sort of optimization problem, and I forgot which one this is.
What does the color mean?
These colors, they're often sort of strength of connections. You can use it in all sorts of different ways. We really Tim, who created this, my friend Tim Davis, he really uses it so that the picture looks really nice. Okay, so we can play with these colors, and there are lots of different ways to color this. But you have to admit this is pretty nice. But I'll show you some others that are really quite interesting. This one is from one of my fields. It's simulation of an ocean, an estuary or a bay, a shallow water. So where the depth of the water is much less than the width of the area that you're looking at. And this doesn't nearly look so nice, but this matrix that comes out is, in this case, was very unstructured, but still it almost has this same feel to it as water. So it's completely accidental, but it's sort of nice, and that's of course why we made it green and blue. And this is a close-up. This one is another linear programming problem, which is one of my favorite, and the close-up, really quite beautiful structures. And this one is actually a social network, which we have labeled the puppy, right? Because it looks a bit like California puppies, and a close-up. And here, what you see here, these puppy, the flowers, they're really clusters of friends. So, really strongly connected friend networks within this large social network. So you can have a lot of fun with this, right? Okay, now we played with something else as well, and I brought a poster attached by Dougie Poohbags. Because I know Alison was going to show a beautiful working diagram, so I wanted to show that we also sometimes do nice things. So here is my artwork, this. And now I gave it already on there what it is, but sometimes I ask people, what are you looking at? And they may say, well, I'm looking at some sort of network or a graph. But this is the LCSH, the Library of Congress subject headers. And so this is the library system that we use in almost all libraries in the world. And what you're looking at are library main categories of books and their subcategories and how everything is linked together. Now the LCSH, or the Library of Congress, asked us in 2005, me and a group of my students, to help them understand the structure, the graph structure of the Library of Congress. So here were people, catalogers, who had worked on this library cataloging system for decades, and they'd never seen it. They just put in their own categorization. They go in, they say, okay, that belongs to that, and that belongs to that, and these are connected, but they've never been able to visualize it. So we used exactly the same sort of program as you just saw to create a picture of this, and we call it the galaxy, the LCSH galaxy. Now we made it interactive, and I will make sure that Pierre gets the link, because he can play with this. And so you can go in and zoom in and click on a node, and it will jump up and it will show you connected nodes, and this is a way to browse. What was also really funny here is that you see this whole mess in the beginning, in the middle. Now this is all very strongly interconnected stuff, right? So you have to go quite deep in order to really see relationships. We put in words where the categories were strongest, meaning they had most books or other types of library items associated with them. But the library also used it to find lazy catalogers. Because look at this, we call this a supernova. This is Japanese antiquities. And it has one main category and a whole bunch of subcategories. But this cataloger did not interconnect the subcategories. He said, we have Japanese antiquities and 140 things attached to it, but how these 140 things interrelated, he didn't put in, or she didn't put in. So the library can look at this and say, well, we really should be doing something about this, because the more messy it looks, the better it really is for browsing purposes. But we just thought it was a beautiful picture. And again, this took a long time to create. We had to think about how to color so that it would jump out. We had to think about how to sufficiently repel some of these nodes from each other so it wouldn't all look like this. And now we're looking for ways to do this in 3D so that you can truly fly through the galaxy, and maybe even do the same with Wikipedia or any other type of network that you have. You can say, let's go on a flight through my social network, right? And see, and then of course discover that somebody else is stronger connected than you are, that sort of thing. But anyway, it's a lot of fun to play with. So I'll make sure that you have this link, and I'll take any questions you have.